Welcome to today's lecture. We have been discussing about the applications of fluid inclusions in different areas of geology, and you may please note that in this part of the lecture series, the attempt is to bring in cite as many case studies as possible to impress upon the fact that the imprint that is left by the fluid in course of its activity in crustal processes can be retrieved and interpreted in terms of its role in various geological processes. And although it is not possible to give exhaustive coverage of the application of fluid inclusions in these areas in which the fluid inclusion data can be effectively utilized, but attempt has been made to cite as many case studies as possible, and keeping in mind that the Indian examples are also discussed. So, in that context, we just started to discuss one of the important aspects of fluid inclusion studies in application to understanding of deformation in rocks that are brought about by different tectonic forces, and as we see them, analyze them in different situations like collision zones, orogenic belts, the mobile belts, ancient as well as the modern, where the terrain evolved by multiple processes of such activities. And the discussion we just started to understand about how the concept of fluid inclusion planes is being applied to unravel or to understand the deformation process, and at the same time how the fluid has assisted the process, because invariably in many situations in the crust, the processes that take place in a fluid present situation, and the fluid plays an important role in such processes. So, we just quoted one of the work that is referenced here, and as emphasized that fluid inclusion, the work on fluid inclusion plane or fluid inclusion planes do have a very good future and need to be applied or need to be studied in many different terrains where they have not been done, so that many important conclusions and many important and interesting interpretations can be made to understand the process better. So, here continuing with the point from where we left in the last class, taking up the same case study as the Hercynian granite in the northwest French massif, where these authors presented their work using fluid inclusion plane to understand the stress analysis, these conditions of stress during the deformation process. And needless to mention that the fluid inclusion work have to be adequately backed up by analysis in the study as well as in the laboratory on deciphering the directions or the nature of the far field stress conditions, which are essentially represented in form of the principal stress axis, the stress ellipsoid, the maximum, intermediate and minimum principal stress axis represented by sigma 1, sigma 2, sigma 3, and those kind of calculations are also made from the structural data obtained in the field from the slip of on the fault plane and many other kind of features that are measured in the field. So, we will restrict our discussions to as and when the fluid inclusion have been considered, and the fluid inclusion study has contributed to this particular piece of work. So, during their study in the French massif, it was interpreted that it was essentially a northeast southwest compressional force that acted in the region, which manifested. There are, if this diagram, it represents that there are many different fluid inclusion planes oriented in many different directions, out of which the northwest southwest southeast fluid inclusion plane with almost vertical to subvertical deep are the most prominent fluid inclusion plane, although there are later episodes of hydrofracturing or the brittle fracturing and opening up of this fracture mode 1 kind of fracture and giving rise to fluid inclusion planes in later stages. But for the time being, concentrating on this particular set of fluid inclusion plane which are associated with the main deformation phase was considered. So, here the background analysis has been done, the stress ratio is known, and this particular fluid inclusion plane was found to have dominantly aqueous biphase inclusions, which homogenized in the range of 270 to 320 of almost as an average of 300 degrees Celsius, and the salinity depression in freezing point was about -1 degree Celsius, which could be calculated to roughly about 1.88% NSAID equivalent. So, as we know that many of the situations where the deformation takes place in the presence of a fluid, there we do not have an exact quantitative idea about the effective vertical stress, because the pore fluid pressure plays a role. So, then here the fluid inclusions, they help us in having some idea, at least a range can be interpreted in terms of a range, that what could have been the fluid pressure. So, if these inclusions were considered, the temperature of homogenization and the salinity from which the densities could be calculated and the isocores could be plotted, and the taking on this kind of an average value for these isocores, and the authors here, they interpreted that it was giving kind of a 50, roughly about 50 plus minus 10 megapascal, that means 500 bars of pressure, which could be interpreted from analysis of this particular fluid inclusion plane. And if this particular the 50 megapascal is converted to, considering that it would have to be a hydrostatic condition, then it would be translated into a depth of about 5 kilometer from the surface, and that 5 kilometer from the surface, if the taking at the granitic terrain where the rock is essentially granite whose specific gravity is known, then the lithostatic pressure could be also calculated, which could have been give an idea about the vertical stress there, which come out to be around 130 megapascal or about 1.3 kilobar. So, normally we are interested in actually getting the value of the sigma 1 minus sigma 3, that is the difference between the maximum principal stress and the minimum principal stress values, and that actually is an important parameter in understanding the deformation process in any segment, any crustal rock. So, that happens to be a function of these parameters, such as this ratio, which this ratio is essentially the ratio of sigma 1 sigma 2 minus sigma 3 divided by sigma 1 minus sigma 3, and that ratio, as I mentioned before, could be calculated from the stress analysis data, and this mu is the static friction, and the lambda is kind of an effective stress, which is essentially the pore fluid divided by the vertical stress here, which takes on a value of 0.4 if the stress is hydrostatic, and it becomes 1 if it's lithostatic. So, now if this under this condition, this diagram shows that this is a on this plot of sigma 1 minus sigma 3 versus lambda v. Here, if we take a range of take a value of consider the value of hydrostatic pressure and take the value of lambda v as 0.4, then these extreme lines represent the lines which are constructed by taking different sets of value for this friction and the values of the R, that is the ratio, stress ratio, and then some kind of range in the sigma 1 minus sigma 3 could be constrained from the value of R and the mu. This is the friction and the stress ratio that is calculated. So, if one considers the lambda v to be around 0.4, and then it actually gives an idea that the value could be around 70, that is indicated by this arrow here, between 70 to 105 megapascal could have been the condition of effective stress that would have acted in the process of deformation. So, these are the ones which essentially can be it could only be made possible by looking at the fluid inclusion planes and then having the calculation. So, the accuracy of such kind of values will always be depending on the calculation of the densities, isocores of the fluid inclusions and the constraining of the pressure value from the isocores. The better the constraints are, the more accurate is the final value of the this parameter that we can get. To take it, it would always be interesting to cite some of the case studies which have been done on the Himalayas, and one such description, it has not been very rigorously analyzed, but some description of fluid inclusion planes and correlating it with regional tectonics can be cited from the work of Boulier 1999, and as I have said, a list of all these references will be provided at the end of this week's lecture for the details to be referred to, but these only here we intend to give a broad overview and brief idea and bring home the point about the importance or the implications, useful and important implications of the study of fluid inclusions in understanding crustal processes. So, the background is we all know it is a series of southward dipping thrusts, northward dipping thrust and the southward thrusting of the different segments, the segments of the different piles of sediments of the lesser Himalayas, the central Himalayas, crystallines and so on. So, this what was done in this particular work is the syntectonic and the syn-metamorphic quartz lenses in the rocks around the MCT from below and above the sediment piles of the MCT were studied, and here the direction and the proper care has been taken for the proper referencing of the oriented samples on which the fluid inclusion planes could be very well referenced with respect to the regional stress direction. So, what was observed was that there were aqueous carbonic fluid inclusions along healed cracks with increased CO2 concentrations to the as the MCT is reached, which will be showing in the next slide. Density and the isochore positions do not conform to the peak metamorphic condition, rather density change brought about during uplift and exhumation. So, these particular fluid inclusions that were studied and were not exactly conforming to the peak metamorphic conditions, and this H2CO2 fluids, they result from the metamorphic devolatilization of the lesser Himalayas. So, the aqueous carbonic inclusions that was seen in the fluid inclusion planes in the from the syn-metamorphic quartz lenses that were sampled, they are presumed to be the result of the metamorphic devolatilization of the lesser Himalayan formations below the MCT, and the late aqueous fluids were of meteoric origin, were interpreted to be of meteoric origin. So, this was the situation here. If this is the MCT, then samples which were taken from below and above. So, here mostly the FIPs that were taken were H2O CO2 type, and the late FIPs with on the vertical fluid inclusion planes. So, these the FIP which were having the aqueous carbonic inclusion type were mostly on planes which are parallel to the foliations defining the MCT in that region, and but the FIPs where they're populated out by aqueous inclusions, H2O rich inclusions, were having at vertical or subhorizontal, and aqueous inclusions restricted to the units which are above the MCT. So, what was shown here was that these dotted lines were representing the fluid inclusion planes, and they were mostly emanating from the grain boundaries, and this particular section is perpendicular to the foliation and parallel to the stretching lineation. The FIP is at high angle to the stretching lineation and consistent with the seen metamorphic deformation. So, here what was observed was that the fluid inclusions, they conform to evidence of isothermal decompression that was observed in the late fluid inclusion planes, and was speculated as they are linked to the recrystallization, like the situation which we discussed before in case of the Sardinian examples, where the earlier inclusions which are trapped in the subhorizontal the fluid inclusion planes containing the H2O CO2 type, they were later on recrystallized with the recrystallization of the host quartz, and evidence of the isothermal decompressions were observed in them. So, there were no much of microthermometric data or PVTX data and isocores that were presented in this particular work, but it was qualitatively shown that with the progress and towards the later part of the exhumation history, this isothermal decompression were also imprinted in form of the differently oriented aqueous inclusion, and the original homogeneous aqueous carbonic fluids were entrapped in the fluid inclusion planes which are indifferent at high angle to the grain boundaries. This particular case study is from an orogenic gold deposit in Abitibi province, Canada. Now, this is a interesting case study that was presented in this again by Boulier 1999. So, we could possibly just have a little bit of a background idea about what exactly happens in a orogenic gold formation system. So, what is essentially is that the regional far field stress operates on a horizontal direction. It is a compression axis, it is a compression horizontal compression that operates there with the maximum principal stress direction as horizontal, and the system evolves in this way that there is an impermeable barrier which makes the fluid to be confined within this particular region, and the fluid which is generated in the process of devolatilization of the rocks, the volcanosedimentary pile, the greenstones which are generally the rock types in orogenic gold systems. There the fluid which is essentially will be a homogeneous aqueous carbonic fluid, that fluid which is generated here in this particular compressive regime, it keeps on accumulating, and because of this impermeable barrier, this fluid is not able to be channelized through the through whatever is available, as it could be a fault system, and within that process the fluid is actually the fluid pressure exceeds the lithostatic pressure, and which is called as the supralithostatic pressure, and during that kind of a period, because the fluid is developing a supralithostatic pressure to withstand the load of the overlying rock strata, and is this particular structure is an unfavorable structure for the fluid to move through. So, it waits till the time that there is a seismic rupturing or a failure, through after which the fluid escapes through these channel ways, and there is a drop of the fluid pressure, and the operating stress system undergoes a change in their orientation. So, during the process in which the supralithostatic pressure builds up, there are generations of this kind of subparallel subhorizontal kind of vein system or the flat vein systems, because of the hydraulic fracturing that takes place. This particular process, as it has been presented by many in the literature, that it keeps on in a repetitive manner, concomitant manner, that with initial phase of the rupturing and the release of the fluid, decreasing of the fluid pressure, the fluid escapes through this particular zone and then deposits the quartz veins along with the with gold, and then after this particular zone by the deposition of the quartz veins gets sealed up, again it leads to the development of the supralithostatic pressure in the fluid, which is again below that. So, it keeps on happening in a cyclic or a repetitive manner, which has been presented as the seismic pumping or the fault valve mechanism, and the veins which form in this process, they are being described as the crack seal kind of processes. So, what is expected here is that there will be one state in which this supralithostatic pressure will create hydraulic fracturing and generate this kind of flat veins by brittle failure, and then it will be altered. Then after the fluid has escaped, the fluid pressure has dropped, the stress condition will change and there will be vertical shortening that will be in this kind of veins. So, these veins will experience initially there will be a generation of hydraulic fracturing and opening up of this under a particular stress condition when sigma 3 will be vertical, and then when there is escape of fluid and collapse of this structure and there is vertical stress. So, these veins will give rise to vertical hydrofracturing and crack seal kind of process. So, by looking at the veins, they would always exhibit very complicated pattern or structure. So, this repetitive structure of hydraulic fracturing and then collapsing of these veins, and again another set of hydraulic fracturing and then vertical type of vein, sometimes accompanied by formation of some late hydrothermal minerals like tourmaline. So, this gives this kind of veins give very interesting microscopic features from which such features could be deciphered. So, with this at the background, in this particular work the fluid inclusion planes were studied in. So, here this particular regime represents here or here which is also been shown here, these two stages, that here these veins will be the shear veins. Their orientation will be different from the veins which are here, even though they will be kind of abutting against the main plane of shear or the fault here, and as it has been shown here, there will be extension vein collapse during the time at which the fluid pressure is dropping. So, one would expect then in this case these two different this cyclic manner, this flat vein would preserve episodes of initial stage where there is because of the building up of the lithostatic pressure and the hydraulic fracturing and the generation of these veins, in which sigma 3 will be vertical and the other case when sigma 3 becomes horizontal. And so, one would definitely would see many series of such fluid inclusion planes. At least one dominant plane would be during the process of during the first phase, and then there will be almost perpendicular to that there will be fluid inclusion planes. So, such fluid inclusion planes in these kind of veins in this gold province in Abitibi province of Canada, there are some selected gold deposits from where the veins were sampled, the shear veins as well as the flat veins. So, they were populated with carbon dioxide rich and aqueous rich inclusions with variable proportions of carbon dioxide. So, the author has classified them to be carbon dioxide dominant and water dominant and intermediate inclusion types which variable proportions of carbon dioxide and water. So, the FIPs studied in the extensional the flat veins, these FIPs containing pure carbonic inclusions parallelly vein walls, and the FIPs containing the aqueous inclusions are subvertical to perpendicular to the vein wall, as is expected in the phase in which the fluid pressure is dropped and the stress conditions is just reversed. And the FIPs containing the mixed aqueous carbonic inclusions are oriented also intermediate between the two, for which the exact mechanism is not very well known. So, here the hydraulic fracturing under high fluid pressure, this kind of situation takes place where the fluid pressure will be equal to sigma 3 plus the tensile strength of the rock, and the differential stress would be low, which would be less than 4 times the tensile strength of the rock. So, this is what is the general condition which applies to such kind of fault mechanism of formation of this kind of shear veins and the associated flat veins that is observed in many such orogenic gold mineralizing system in many of the areas, many of the granite greenstone, Archean granite greenstone terrains in many different cratonic blocks, which we discussed before. So, FIPs which were studied in the shear veins were not as very clear as the flat veins, because they have undergone more of recrystallization through the different phases of shearing, which these flat veins actually survived. So, the shear veins, they exhibit greater degree of recrystallization, grain boundary migration. So, there were, as discussed before, there are grains which are inclusion free, the more recrystallized polygonal grains, and many kinds of features as discussed before were also observed here. The fluid inclusion planes containing pure carbonic inclusions at high angle to the vein walls, this as in the case of the flat veins, here also they are at high angles to the vein wall. FIPs containing aqueous inclusions are more complex, also at high angle to the vein wall along the slip plane, and the FIPs containing mixed aqueous carbonic inclusions are at high angle to the vein wall, but perpendicular in direction to the FIPs containing the pure carbonic inclusions. So, the horizontal carbon dioxide rich fluid inclusion planes were contemporaneous with the opening of the veins where sigma 3 is vertical, as has been shown here, and the vertical NaCl H2O fluid inclusion planes contemporaneous with the vertical shortening as has been shown here, and which are likely to give rise to this kind of mode 1 type of cracks, which will be sealed by deposition of quartz veins there. So, the implications of this, the presence of both horizontal and vertical fluid inclusion planes in extensional flat veins imply that they record both extension and vertical shortening, strong partitioning of end member fluids in different sets of healed microfractures. So, what is actually interesting here is that these process actually keep happening in a continuum concomitantly with the seismic rupture or failure, then again build up of the fluid pressure above the lithostatic pressure that we say is a supralithostatic pressure, and then another phase of seismic rupturing and the dropping of the fluid pressure, so that the vertical shortening takes place. So, they are essentially seen depositional or rather than being post, I mean these kind of deformations are not actually, they do not post-date the formation of the veins, but actually they keep on happening during the growth of these veins in different phases, which are very clear from the microscopic observations of these veins and also from the fluid inclusion plane. So, what is interpreted here is that during the superlithostatic pressure, where the fluid is actually a one phase mixed H2CO2 fluid, and they are the ones which dominate the fluid inclusion plane, which are parallel to the vein walls, and as and when there is a collapse of this wall and generation of this kind of walls which are perpendicular to the vein wall, there the H2O component which is unmixed from the parent fluid, and as discussed before, possibly because of their more acute wetting angle. So, those are the ones which actually populate the perpendicular set of the fluid inclusion planes. So, FIP in both types interpreted as a result of concomitant vein growth and deformation, incremental development of extensional veins they indicate alternating episodes of extension and shortening, and the compositional distinctions between these fluid inclusion planes on orthogonal planes can be explained as due to the phase separation during the seismic rupture and entrapment of the aqueous inclusions on vertical microcracks. So, this gives us here the fluid inclusion study of the fluid inclusion plane is gives a very good complement to the analysis that was done from the microstructures of the quartz veins, which show evidence of growth in multiple phases, and also gives as expected the different fluid inclusion planes, the fluid inclusions there being of compositional different types is also very much very well explainable on the basis of the switching over of the stress conditions in this cyclic process. So, we will continue discussing in the next class. Thank you.